What we're going to do in this video is we're going to get a general introduction to solving recursive algorithms and reasoning about time complexities to give recursive functions general bounds. We need to lay this groundwork first before we can get into our recursive problems, because if we can reason about a function and give it a loose recursive bound, then we can look at our specific interview problem implementations and give them bounds. It gets kind of difficult because for certain recurrences, you're going to have to take into account random variables for average cases. You're going to have to solve levels of work for a recursive tree using summations. It's going to get into more nuanced things like algebra with summations, and I don't want to go too deep into that. You would never need to do that in the interview. But I want to show you an introduction to this stuff so that you can learn more yourself and you can know exactly what you need to use in the interview to reason about general recursive time bounds so that you have the answer to the question, what is the time complexity? That's what we're going to look at today for recursive functions. So as I was saying before, we want to model recursion as a tree. Recursion is when a function calls itself. And what a recursive function needs is it needs two things. It needs a base case where the recursion will stop. The base case must be wide enough of a net to catch all types of input that are being converged to it by the recursive case. The recursive case is going to reduce the size of the problem at every single step of the algorithm. You need a base case and a recursive case. Recursive case narrows down the input or the state of the overall algorithm to the base case. What we can put here is a tree so that we can imagine this for a second. As I was saying before, recursion can be visualized as a tree, and the nodes are calls. The nodes are calls themselves, and the edges in this tree are the relationships between the calls. If A calls function B, then B is a child of A in this tree. And then B is going to do its thing, it'll come back to A, and then A will call C, and it's going to proceed, C will do its thing, return to A. A is a function. A is a function with state and logic. These are the two biggest things. I repeat this very often, but if you can understand this, recursion becomes a lot simpler to grasp. When you see every single function as a policy for an overarching algorithm to say, given this state, where does the recursion need to go? If you can understand this overarching way of thinking, then these problems become simpler. Okay, so we've established the base understanding here, that our nodes are calls and our edges are the call relationships, and we have calls that continue down the tree. And the A is our root function call, and then all of these are children. When we have a recursive tree like this, we actually can model the exact amount of work done in any single call, given the input size given to that call. We use a tool called recurrences, and these recurrences model the recursive work done by an algorithm. So let's see what a recurrence looks like. Recurrences are the bread and butter of our ability to analyze recursive algorithms. They allow us to model how much work does this single call do, and then how is it going to defer that work, and how do these calls relate themselves to give us the overall work that the whole recursive tree has done. Our goal is to sum the recursive tree. If we can sum the work done across every single call, we have found the time complexity of our overarching recursive algorithm. Before it was just one. We had one stack frame, and the stack frame did some for loops or something. Easy, summations, one call, everything straightforward. But when everything's broken up into a tree and work is deferred across many levels, we have to take another approach. We need to do a summation of work across these levels of work. So what we have here is a recurrence. A recurrence has the function. Here it's just T of n. It's the work done given an input of size n. This is not the overarching n. Like if I have a string passed in, its length n. This is the input to the recursive call. If I have n, and then what I do is I pass half of the input to the recursive call, the next recursive call, then the n in that frame, the n in that stack frame is n over 2. And then this is n over 2 into everywhere you see n. So we're going to model the whole trees, but I just want to make sure that's clear. This function, given an input of n, it might be string length, it could be anything. What we're going to do is we're going to make two more recursive calls with half of the inputs, n over 2. This n becomes n over 2. Two recursive calls call the same function with half the input, and this plus n minus 1 over here is actually concrete. Here we see a recursive case. Those two extra calls are recursive. They're going to create more calls. This is dealing with the expansion of the tree. But what this deals with is the actual work done in any single call given the input size n. So this is actually a famous recurrence. Well, it's not famous, the algorithm's famous. This is the recurrence for merge sort. Merge sort will cut input in half. It will make two calls, one call for the left side and one call for the right side. When these recursive calls come back, we're going to merge those two inputs, which are size n, and we're going to do n minus 1 comparisons to merge them. If you want the full detail, watch my merge sort video, but this is the actual work done in this call. This whole thing right here is a call. That whole thing right there is a call. We are modeling what is the work for this call given this input size, how does the recursion continue, and what is the actual work done within the call. If we can find a way to solve this general formula for the recursive work, then we have the ability to provide an exact bound on the time complexity. Exact not in the sense of theta, but a very accurate bound. So if you want to get more of a primer into binary trees and all that stuff, I have a video on all the terminology, full, complete, and that stuff. All we need to understand is a full binary tree is a binary tree where each node either has no children or it has 2 children. And a tree is complete if it is filled top to bottom, left to right. If we can understand and reason about how many nodes are in this tree structure, we have the ability to quickly understand general bounds for recursive functions because we can extract mathematical properties from this, and we're going to see exactly what we need to take away. In real life, what we do is we're going to get exact comparisons, exact amounts. We're going to create a recurrence. We would create a summation. We would do all of the algebra, and then we would bound the solution. But in the interview, you don't have time to do complicated math. You're not expected to do algebra and all these summations. You're not expected to do any of that. You just need to understand generally how do recursive functions, how can they be modeled and understood? And a tree is the key to understanding that. There's 2 things that we need to take away from this structure. We need to understand, 1, the branching factor. In this case, the branching factor at every single node is 2. Let's write that down. Okay, we've established every node generally, in this case exactly, will have 2 spawned children. And remember, these nodes are recursive calls. We're trying to understand how recursive calls form, and we want to analyze the work across the tree. The second thing that we need to understand about this recursive algorithm is the depth of this tree. So this tree has 1, 2, 3, 4. It goes 4 levels deep, and it has 1, 2, 3, 4, 5 levels. But the depth is 4. It has 4. It goes 4 jumps downward, which is 5 levels. So the depth is 4. In reality, recursion will not look perfect. It might go all the way down this way, and all of this might not exist. Or maybe this part's jagged. We're going to often overcompensate for that when we're finding our upper bounds. We're going to assume a perfect tree when we find our general bounds. But in real life, we would solve for the exact amounts. But we're not looking for the exact amounts. We're looking for something we can eyeball and quickly understand. So we assume the tree is perfect, and we use these 2 values, you'll see, to find our time complexity as a looser bound. Let's look at the exact amount of nodes in each level. What we want to now do is draw a connection with some sort of formula to the amount of nodes in the whole tree. Because if I know how many nodes are in the tree, and I know how much work is done at every single node, then I can just sum the work up, and then I know the answer to what I can bound. There's 1 node in the top level. Next, in the second level, we have 2 nodes. Next, in the third level, we have 4 nodes. In the fourth level, we have, well, if we 0 index this is level 0, 1, 2, this is level 3, and then the third level has 8 nodes. And then the final level, the fourth level, has 16 nodes. And you might be noticing a pattern here. the amount of nodes in each level follows a pattern of multiplying by 2 every time. 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16. And this pattern is actually something we can generalize to the level that we are on is the amount of multiplications we want to do to the branching factor. So to make this clear, let me number the levels. The top level is level 0, level 1, level 2, level 3, level 4, and correspondingly we have 1, 2, 4, 8, 16. And our branching factor is 2. What do we need to do to know the amount of nodes in every level of recursion if our tree is perfect? We can just do the branching factor to the level because we notice this. 2 to the 0 is 1. Branching factor to the 0 is 1. Branching factor to the 1 is 2. 2 to the 1 is 2. And then 4 is branching factor to this 2 because that's the second level. And we can just say 2 squared equals 4. And then continue on, 2 to the third is 8. And then continue on, 2 to the 4 is 16. All we did was we rewrote everything in terms of these numbers over here. Remember what I was saying. Now we know how many recursive calls are at every single level. We know there's 1 call at the top level, 2 calls at this level, 4 calls at this level, 8 calls, and 16 calls. And here's the intuition behind this. It makes sense. If the first layer spawns 2 calls, and then those 2 calls spawn 2 calls, let me actually write this out. The first level spawns 2 calls, and then let me take into account the first level with a 1. And then the first level spawns 2 more calls. Those 2 calls each spawn 2 calls. Now we have 4 calls. And then those 4 calls each spawn 2 calls. Now we multiply again by 2. Now we're going to have 8 calls in that level. And then we multiply by 2 again. Those 8 calls will each birth a node, leading to 16 calls in the final level. And notice, how many times are we multiplying 2? We're multiplying it 4 times. And that's how many nodes are in the last level. We had 2 calls, each creating 2 more calls. We have 4 calls. We have 4 calls, each generating 2 calls. That's 8 total. And then we have 8 calls, each generating 2 calls. That's 16 total in the next level. Now jumping to actually solving it, like I was saying before, remember, we want to sum the work across all of these levels. And right now, we're only interested in counting the number of calls. We're not interested in knowing the exact work within the call. That's more of a later thing we'll get into. But we just want to see how many calls are in this tree. What this turns into is, let me sum up the calls. 1 plus 2 in level 1, 2 calls. And then in the next level, 4 calls. Remember, we're summing work. How many calls are in this tree? Plus 8 calls in this level, plus 16 calls in the last level. And now I want to transform this into a generalization. And we already began with that. We said branching factor to the level will give me the nodes in the level. That's going to help us out here. We're summing the levels. Let's change this into our branching factor to the level. Let's do that term by term. So the first one, and then the next one, 2 to the 1, and then the next one, 2 to the 2, and then the next one, 2 to the 3, and then 2 to the 4. And we can actually continue summing, and then we generalize it. 2 to the n. We say 2 to the 0 plus 2 to the 1, 2 to the something, 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 to the n. N depth. And this is actually ringing a bell. If we have a string and we decompose it character by character, we're going to go n calls deep at maximum if we keep pushing on stack frames. And this might help us in that case. What we actually can do is we can notice what is the range of this summation. 0, 1, 2, 3, 4, dot, 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 and then n. So this goes from 0 to n. We're trying to sum. We said our summation goes from 0 to n, and don't worry about this notation. This just means from 0 to n, take the repeated sum of what is inside here. So it's called a summation. So let me write it. All this does is it injects a value into an equation. And I forgot variable. We inject this variable I into the equation for values 0 to n. So I inject I as 0, I inject I as 1, I inject I as 2, inject I as 3, and finally at the end I'll inject I as n, and I take the sum of all of those quantities. And what is our inner equation? It's 2 to the level. It's the summation of 2 to the 0, 2 to the to the 1, 2 to the 2, 2 to the 3, and we sum all of those. This is just the notation for it, of what we just did. And what we can now do is we actually can solve this. And I don't want to get into the actual algebra of solving it. For this is actually something called the geometric series, and there's a special way you can solve it. We don't want to worry about algebra. We just want to pass our interviews. So we can just throw this in a calculator and we'll see that we get this. Ultimately, when we solve the summation, we get the total amount of nodes in this tree is 2 to the n plus 1 minus 1. So imagine this. If n is 0, we have 0 plus 1 is 1. 2 to the 1 is 2. 2 minus 1 is 1 node. If we have 0, 0 depth. If we have a depth of 1, that means we're going to go deep 1. We're going to have everything up to there. We're going to have above depth of 1. 1 plus 1 is 2. 2 to the 2 is 4. 4 minus 1 is 3. 3 nodes, 1, 2, 3. And if you keep generalizing this, you'll see this is actually true for this whole tree. If this tree is perfect, this is the exact amount of nodes that it can have at maximum. And this is actually interesting because our upper bounds are considered with maximums. This is the perfect equation for us to draw an upper bound. And we actually, disregarding any of the work in these recursive calls, imagine they do constant work, just O of 1 work. We can bound the actual amount of recursive calls to big O of drop the constant, n plus 1, only the n is the dominating factor there. It becomes big O of 2 to the n. We drop that minus 1 as well. So what we're saying is this function right here, this function that gives us the exact amount of nodes in this perfect tree, for a branching factor of 2 is this, and it's an element of the class of functions that are upper bounded by 2 to the n. This is just fancy notation for element of. This function is an element of this class of boundings because we're bounding that dominant term. And all we needed to know was the branching factor, which was 2, and the depth, which, if this is a decomposition of a string where we decompose character by character and we go n calls deep, it becomes 2 to the n. And that's our upper bound. This is where generally we're going to get our upper bounds, imagining it's a perfect tree. So if you're in an interview, this is what you do. If you get a recursive function and you can approximate the branching factor, say, hey, interviewer, the branching factor here is 4. We're going to go n calls deep. So if we assume this is a perfect binary tree, we can make a blanket bound that is not mathematically tight, but it will be accurate based on this loose assumption our recursion tree is perfect like this. I can just give it a general bound of branching factor to the depth. And this is our general bound we can do. And yeah, this is something really useful. This is something that you can take with you to other problems. And it's never going to be this clean. It won't ever generally be this clean, but this gives you a step to understanding this. This is a step to have a general ability to bound functions. Let's imagine the branching factor is 4. What would the sum look like? If the branching factor was 4, we'd take the sum from I equals 0, 0 to n, and we would say branching factor to the level. So 4, which the branching factor is 4 to the I. And if we solve this, we see again that our rule holds here. 1/3 4 to the n plus 1 minus 1. What that means is this constant disappears. If we want to see what class of boundings is this an element of, we have 1/3 times 4 to the n plus 1 minus 1. First off, we can immediately drop the constant here. We can drop the constant because we're looking for asymptotic complexity. And it's inherent to the definition to inject a constant. If you see my video on that, you'll get a really deep understanding into that. There's really no point in having a constant in front. We can remove it. And yes, we're modifying the original function. That's fine. We now can remove the dominated term. Minus 1 gets removed. And then we see, if I add 1 to this, it doesn't really change the behavior. It's still 4 to the n. That plus 1 is effectively dropped at very large n values. Ultimately, our original function is a part of the family of 4 to the n, big O 4 to the n. Again, is this the tightest bound? No, it's not going to model the recursion exactly. But the big O 4 to the n is a good answer. It is a good starting point without pulling out algebra, without pulling out summations. And if you're in an interview, I'd say this is all you'd be expected to know. Beyond this, you would have to actually solve the exact equation, and you'd have to understand how to do crazy stuff. You'd have to, if it were an average case, you would have to do summations, you'd have to do randomized variables. There'd be so many more things you'd have to do that you wouldn't be expected to in an industry interview. Just generally understand how recursion works, how can we bound, assuming it's a perfect tree. And I would state to your interviewer that this is a loose bound, this is not perfect, but these are my understandings. The branching factor is 4, my depth is n. This is a general bound. So this is the basis I want to draw for recursion. So when I go to time complexities, I don't just want to assume you're going to, it's intuitive. I want to lay this basis so that we can all be on the same page about why a certain base is the case, why a certain exponent is the case. And now let's look at an example where the bounding does actually fail us. It actually isn't as exact as we want. It's called the Fibonacci sequence, and you're probably familiar. Let's look at the code. So now what we have here is something called the Fibonacci sequence, and we're given an input of n, and it wants you to generate the sum of the sequence up to n. I don't know if it's including or excluding. I'd have to think about it more, but the core concept that I want to demonstrate is how do we look at this and say, what is the time complexity here? What is the work done in this call? All we're doing is we're returning values, we're doing arithmetic operations. All that's going to be is constant. That is constant. These are machine operations within the registers. None of this is something that scales with the input. It's just going to be constant, no matter how big the input is. What we do want to understand is what are the recursive calls? The recursive calls are here. We see that the recursive calls reduce the original input to converge to these base cases. And what we can reason here is that every call generally it's going to want to make 2 more recursive calls. That does make sense. We're going to make 2 more recursive calls at every single node. The tree would kind of look like this in our assumption. And this reminds us of before. Before, the branching factor is 2. The depth, what would the depth be here? Well, who's going to drive us? What is the pace that's going to drive us the deepest? And if we continue to reduce the size by 2 every time, by 2, by 2, I'm not going to get as deep as if I'm much slower in the reduction of input size. If I'm reducing n by 1 every time, this side of the call, this is going to be a deeper tree because it'll have more reductions going downward versus 2. 2 is going to reduce and get to the bottom faster. It's going to get to 0 faster than reduction by 1. This leads us to having an uneven tree. We would reason that this is big O2 to the n, right? We're using our blanket approach from before. We understand that how many nodes would be in this perfect binary tree. The number of nodes in this perfect binary tree, if the branching factor is 2, means it's going to be 2 to the n plus 1 minus 1. We found that before, but this is a loose bound on a heavy assumption, a blanket assumption of a perfect tree. But the recursion doesn't turn out to go that way. The recursion turns out to be a bit more jagged. Let's actually model it right here to see. Let's imagine n equals 5. If n equals 5, the answer to the subproblem with n equals 5 is the answer of the addition of the subproblems of n equals 4 and n equals 3. And now, the answer to this subproblem is n equals 3, n equals 2. And then the answer to this is n equals 2, n equals 1. And then this n equals 1 over there, that's actually a base case. It'll return. This n equals 3 spawns stuff out. So let's just fill out the rest of these. And this is what a recursion tree looks like. And do you see a gap? Before we made the assumption that all of these would be filled, but there's actually a huge hole in the tree. All of those calls right there are missing. Our big O of 2 to the n bound made the heavy assumption that those calls would exist, and if this tree were absolutely huge, like very large, there would actually be a huge hole there. And this is what I was saying before. In this case, we would draw a recurrence. We would solve the exact recurrence, and our actual value we would get after doing all of the algebra, all the summations, we would get about 1.61 to the n as the upper bound. I think this is a really solid introduction to get your feet wet in recursive time complexities. Again, it gets a lot more complicated when the tree the heights are uneven. It gets more complicated when the branching factors vary. It gets more complicated when the work done in different calls vary. It's more complicated, and you would not need to do it in an interview. In an interview, it suffices to say, this is upper bounded to big O of 2 to the n because of everything we've learned before. So this is a great primer, I think, into recursive time complexities. I hope I did everything right. I hope there was no math error. But now I think we can tackle our recursive problems confidently, and we can derive general bounds to these problems if we know the branching factor and the depth of the tree.